So our goal here is to look at how to graphically solve a system of linear equations, meaning how to think of a system of two linear equations as a graphing question and then use the graph to at least get an approximate solution to this system of equations. So taking a look at what we have here, we have two equations, 3x plus y equals -6 and y equals 1/2 x plus 1. And the question is, how do we find a ordered pair x comma y, in other words, a value for x and a value for y, which is going to satisfy both of those equations simultaneously? The question prompt asked us to graph the system and write its solution. So what's our strategy going to be? Well, we're calling it a linear system because each one of these equations that we're asked to solve simultaneously is a linear equation. If we were to graph each one of them, we would get a straight line. And so our strategy should be to do just that. To graph each of these equations, each one's going to give us a straight line. And if we want to find an x and a y that simultaneously solve both equations, what we should be looking for is a point which lies on both lines. In other words, the intersection of these two lines. If two lines do happen to intersect in a single point, then that single point will be the solution of this linear system of equations. So the first thing we want to do is to either use the x and y intercepts or use the intercept and slope to graph each line. And depending on the form of the equation that we're given, one of those approaches may be easier than the other. But at this point, we have some practice on how to graph linear equations, and so use your instinct, whatever is most comfortable for you. And then once we've graphed each one of those lines, we should be able to tell, hopefully if our graph paper is big enough, whether or not they intersect in a single point. If they do, then we're going to label the coordinates of that point of intersection, and that's going to be our candidate for a solution to this system of two equations and two unknowns. The problem with graphs is that while a picture is worth 1,000 words, you can't always believe your eyes necessarily. And so it's a situation that Ronald Reagan used to famously say, trust, but verify. You can trust that there's a solution to this system of equations, but unless you're able to verify that it works, we can't be absolutely certain on how exact that solution is. So we'll check our solution by plugging the point of intersection into both equations just to verify that it works. So let's get started by graphing each one of these two lines, 3x plus y equals -6 and y equals 1/2 x plus 1. We may take a couple of different strategies for graphing them in either case because we're given equations in different forms. Starting with the first equation, 3x plus y equals -6. This is a linear equation in what we typically call standard form, ax plus by equals c. Y hasn't been solved for on its own. So because it's in standard form, let's take the approach for graphing it where we find its x and y intercepts, then we just plot them on the graph and connect the dots. So if I want to find the y-intercept of this equation, I should set the x-coordinate equal to 0. 3 times 0 plus y equals -6. And then just solve for y. And when I do that, I get y equals -6. So that the y-intercept for this particular equation is the point 0, -6. To find the x-intercept, I'm going to do the opposite and set y equal to 0. There I'll get the equation 3x plus 0 equals -6, which I can simplify to 3x equals -6, and then solve for x by dividing both sides by 3. That'll give me x equals -2, meaning that the x-intercept for this particular line is the point -2, 0, the point where x is -2 and y is equal to 0. So for this first equation, we now know what its x and its y-intercepts are, which means we can plot those 2 points on our graph paper, 0, -6, the y-intercept, -2, 0, the x-intercept, and then just by connecting those dots, we've graphed this first line. What about the second line, y equals 1/2 x plus 1? Well, this equation has been handed to us in slope-intercept format, y equals mx plus b. We can tell because on the left-hand side, y is sitting just alone by itself. And on the right-hand side, we have a completely simplified expression where one term has an x factor in it and the other term is a constant. This allows us to, first of all, identify the y-intercept right off the bat. It's the b in y equals mx plus b. So in this example, that's the constant term. It's the number 1. So the y-intercept of our second line is the point where y is equal to 1 and x is equal to 0. We can also, from this form of the equation, identify the slope. It's the coefficient of the variable factor that has an x in it. So in this example, the m in the mx plus b is 1/2. Well, remember what that lets us do. How do we interpret a slope? Since a slope is a quotient, a ratio of rise to run, of vertical difference to horizontal difference, if our slope is 1/2, we can think of that numerator of the fraction, that 1, as a movement up by 1 unit, and the denominator, that 2, as a movement right by 2 units. So the rise is 1 and the run is 2. That's going to let us stair-step our way from the y-intercept that we know to a second point that we don't know right off the bat. So to graph this line, we'll start by plotting its y-intercept, which we determined was 0, 1. Then we can use the slope to stair-step our way up 1 unit and to the right by 2 to find us a second point, which in this example has coordinates 2, 2. And then connecting those dots gives us a graph for our second line. So far, so good. We've used whatever techniques we need to graph each one of the linear equations that we started with. Now, what are we looking for in this problem? We're looking for the coordinates of the point of intersection of these two lines. And from this graph, if we've drawn this graph carefully enough, it looks an awful lot like that point of intersection has coordinates -2, 0. So that's going to be our guess. That's going to be our most educated guess for the solution of this system of two linear equations. But because we solved this system graphically, we can't completely trust our eyes. If we drew this graph just a little bit off, -2, 0 might not exactly be right. It could be -1.9, 0.1, or something else really close to -2, 0, but not necessarily exact. That's the limitation behind graphical techniques in general, is they can only give us a pretty good idea of the coordinates of a point. So if we want to be sure whether this is actually the solution, we need to check our answer. Let's check that -2, 0 actually solves simultaneously both the equation 3x plus y equals -6 and the equation y equals 1/2 x plus 1. So in the first equation, 3x plus y equals -6, I need to substitute a -2 for x and a 0 for y. Likewise, in the second equation, substitute a -2 for x and a 0 for y. And then just make sure that both of these equations are balanced. Well, in the first equation, the left-hand side, 3 times -2 plus 0, that indeed simplifies as -6 plus 0 in the order of operations, doing our multiplications first. Likewise, the second equation, 1/2 times -2, simplifies to -1, doing all our multiplications first. And now that all our multiplications and divisions are done, we can do our additions and subtractions. -6 plus 0 in the first equation becomes -6. -1 plus 1 in the second equation becomes 0. And lo and behold, the point where x is -2 and y is 0 satisfies both of our equations. It makes both of our equations balance. Therefore, -2, 0 really is the point of intersection between these two lines. So the graphical technique for solving a system of linear equations involves merely taking each of the linear equations that we start with and graphing it. It's going to be a straight line on our coordinate axes. In this example, because one of our equations was in standard form and the other was in slope-intercept, we used a couple of different strategies for graphing those lines. We plotted the intercepts of the first, and then the y-intercept and used the slope of the second. But regardless of which techniques that you use, you're going to get two lines and then look for their point of intersection, which in this example we saw was approximately at the point -2, 0. But we can't be satisfied with approximately. We also have to check our answer. So we took x equals -2 and y equals 0 and substituted them into our original system and actually verified that that point x comma y solves both equations and therefore is what we call the solution of this linear system.